In this video, we're going to talk about diagonalization. Okay, so we're going to focus first on an example that will tell us what's going on in general. Okay, so suppose that we have some 2x2 matrix with a basis of eigenvectors. So in this case, our eigenvectors are 1, 1, and 2, 1, and they have eigenvalues of 2 and 1/3. If we take any old vector, so in this case, we're going to look at the example x equals 4 times v1 plus 2 times v2. Knowing the way to write this vector x in terms of our eigenvectors makes it easy for us to compute a times this vector. Right, because we can write this as a times 4v1 plus a times 2v2. And these guys are each eigenvectors. v1 and 4v1 are eigenvectors with eigenvalue 2, and v2 and 2v2 are eigenvectors with eigenvalue 1/3. So we get the first one is multiplied by 2, and the second, when we take a times 2v2, we get 1/3 of this. And we see this in general. So whenever we have a vector that's expressed in terms of v1 and v2, if we take a times this linear combination, it's just going to be a times c1 v1 plus a times c2 v2. And c1 v1 is an eigenvector with eigenvalue 2. c2 v2 is an eigenvector with eigenvalue 1/3. So we just end up multiplying the first part by 2 and the second by 1/3. This allows us to express the answer in terms of these eigenvectors v1 and v2. Okay. So we see that something's going on with the coordinates here. So if we were to write these vectors in terms of this basis, v1 and v2, there's like a strong pattern of what's going on here. So just a quick reminder of what that looks like. The coordinates for the vector x in this basis just tells you the weights. So how much, what weight we have in front of v1, and then what weight we have in front of v2. So this vector x we would write as having coordinates 4, 2. And when we look at ax, the coordinates there, what did we do? The number in front of v1, the weight in front of v1, got multiplied by 2. That becomes 8. And the weight in front of v2 got multiplied through by 1/3. So now that's 2/3. Okay. And more generally, when we had this linear combination, right? So v1, v2 form a basis for R2. So every vector can be written in terms of these guys. These weights are c1, c2. And when we look at a times c1, b1 plus c2, b2, what did we see? We saw twice c1 plus 1/3, and then 1/3 c2. Okay. So we can think of this transformation as happening where we take the vector x and we multiply by this matrix A, and that gives us AX. But we can also think about what's happening in terms of coordinates. So that was our weights. So if we started with the vector x, when when we look at the coordinates of AX, what did we do? Well, our first coordinate got multiplied by 2, and our second coordinate gets multiplied by a third. In fact, there's a matrix that will carry this out. So if we have AX, the coordinates here are equal to a diagonal matrix 2, 0, 0, 1/3 times the coordinate for X. What's happening when we take our first component, C1, gets multiplied by 2, plus 0 times C2. So we just see that that first coordinate gets multiplied by 2. The second coordinate gets multiplied by 1/3. And this matrix that accomplishes this is diagonal. Notice those eigenvalues show up on the diagonal. Okay. So we have these two different paths. So we have, we can multiply X by our matrix and get AX, or we had this nice simple relationship for the coordinates where we said, okay, if you know how to write your vector X as a linear combination of those vectors, then we'll just multiply the first coordinate by our first eigenvalue and the second coordinate by our second eigenvalue. And there's a way to translate between these, right? So if we have coordinates, this tells us our weights, and we can go from coordinates to the actual vector it represents using our coordinate matrix, CB. Okay. So this translates from coordinates from weights to the actual vector. And how does it do this? If you remember, this this matrix is going to just have the columns V1 and V2, our eigenvectors will show up as its columns. So for instance, if we started out with 1, 0, and we multiply this by V1, V2. Okay, well, in coordinates 1, 0, weights 1 and 0 says we want 1 copy of V1 and 0 copies of V2 and sum them. Okay, and so the coordinate for V1 is just 1, 0. All right, and similarly, if we took V1, V2 times 0, 1, so these are the set of weights, we get just the vector V2. Okay, and so we see two different paths to getting to the same result. So to go from X to AX, one way to approach this is by multiplying by A. A second way is to think in terms of these coordinates. So first we change from X to the coordinates of X. So how did we write X as a linear combination of our basis? Then, once we've written it in terms of coordinates, we just multiply through by this diagonal matrix, which has just the eigenvalues. So basically just stretching along those directions, eigenvectors. And then we go from coordinates back to the actual vectors. And this produces the same output. Okay. We can read this off. This yellow path is the same as our blue path. It says that A is equal to, well, first we're going to do this inverse coordinate map. Then we're going to take this diagonal matrix. We'll multiply by our diagonal matrix, and then we'll multiply by our coordinate map. This coordinate map is often written with as a P. And this coordinate map is just the eigenvectors. Okay. Alrighty. So let's take a look at an example of this. Here we had eigenvectors and their corresponding eigenvalues. So let me just move this out of the way. So we've seen that A is going to be equal to this coordinate map times D times the inverse coordinate map. The coordinate map is made up of these vectors, so 1, 1, and 2, 1. Our diagonal matrix has our corresponding eigenvalues. So this eigenvector 1, 1 has eigenvalue 2, and the eigenvector 2, 1 has eigenvalue 1/3. Okay, so we've got one more piece to find, which is what this inverse, the inverse of the coordinate map is. So we do 1 over the determinant of CB. We switch the diagonal entries and negate the off diagonals. So this is 1 over 1 minus 2, 1 over negative 1 times 1, negative 2, negative 1, 1. And so we end up with negative 1, 2, 1, negative 1. Okay. Okay, and we're able to now write down A as a matrix multiplication. So it's going to be equal to 1, 1, 2, 1 times this diagonal matrix times the inverse of our coordinate map. Matrix multiplication is not commutative, but it is associative. So we can either multiply these two together first, or we can multiply these two matrices together first. I like to start on the left. And so we're going to be writing down this matrix described by these eigenvector eigenvalue pairs. Okay, so we're going to multiply. We have 2 times the first column. So we've got 2, 2. And we have 1/3 times the second column. So we have 2/3, 1/3. Times negative 1, 2, 1, negative 1. Okay. We multiply again. We have negative 2 plus 2/3. So negative 6/3 plus 2/3 is 4/3. We have 4 minus 2/3. So 12 minus 12/3 minus 2/3 is 10/3. We have negative 2 plus 1/3 is negative 6 plus 1/3, negative 5/3. And then we have 4 minus 1/3. So 12/3 minus 1/3 is 11/3. Okay, and so this is our matrix A. All right. So one more time. So the idea with diagonalization is that we have this really easy picture that if we're looking in the direction of our basis of eigenvectors, our multiplication by our matrix just looks like stretching or reflecting in that direction. So we see just a really easy matrix. It's diagonal. So in our case, we were stretching by a factor of 2 in the V1 direction and compressing, so multiplying by 1/3 in the V2 direction. Very simple transformation here. And so we can relate these two by saying that we can first change from x to its coordinates, then we apply this transformation, and then we change from coordinates back to vectors. Okay, great.